Welcome back, Physical Science 20. So we'll now look at real image defects in concave mirrors. So we looked at the scenarios involved with object placement beyond C, at C, inside C and F. Now we'll look at some image defects that can happen. So in tracing rays, you have reflected rays the rays from the principal plane, which is a vertical line representing the mirror. Okay. In reality, rays are reflected off the mirror itself, as shown in figure A on the right. So if we did it this way, depending upon the curvature of the mirror, we could get scattering all over the place. If angle I equals angle R for each of these rays, what we see here, depending upon the shape of the mirror, how much the curve is, they may not reflect all through that F area. So notice that all parallel rays that are close to the principal axis or periaxial rays are reflected through the focal point. Other rays converge at points closer to the mirror. The image formed by parallel rays reflecting off a spherical mirror with a large mirror diameter. So if it's a large mirror diameter and a small radius of curvature is a disk, not a point, this is called spherical aberration, which makes the image look funny. And it's due to all parallel rays are not reflected through the focal point F. A mirror ground to the shape of a parabola, as seen over here, though, suffers no spherical aberration. Because the cost of manufacturing large, perfectly parabolic mirrors, many of the newest telescopes use spherical mirrors and a smaller, specially designed secondary mirrors or lenses to correct for spherical aberration. Also, spherical aberration is reduced as the ratio of the mirror's diameter above to its ratio of curvature is reduced. Thus, a lower cost spherical mirror can be used in lower precision applications. So if it's made more parabolic, we can see that all the reflection goes through the focal point. Okay, so we looked at real image here, the images that form because the reflected rays intersect at a point. Let's look at virtual images of concave mirrors. You've seen that as an object approaches the focal point, F, a concave mirror, the image moves farther away from the mirror. If the object is at the focal point, all reflected rays are parallel. But before we do that, maybe we should look at the case in which, so we looked at beyond C, at C, in between C and F, and now we're going to look at inside F, but we didn't look at the case of at F. So I'm just going to grab a piece of paper and we'll figure that out. So if we look at the scenario when it is at F, so I just sketched this out on another piece of paper. You can do the same if you like. So, of course, the first ray is in parallel out through F. Okay. And another line that we can draw, now we can't go in through F, out through F here because it's at F, but there's another third ray that we can look at. For example, when if we have a ray going through C, just like on the principal axis, if I had a ray go through C, hit the mirror, it reflects back upon itself. So if I was to go through here, for example, if I was to go from C, hit the tip of the object, it would hit the mirror, then reflect back on itself. And if we notice what happens here, I tried to draw as best I could here, but these will be parallel reflected rays. So they extend on forever. They never cross. So we could say the image is at infinity. So for all intent and purpose, we can say that there is no image formation when it's at F. Okay, so that's an example that we didn't do. And maybe I should have included it in there. So if we have, because before there we looked at if it was in between C and F, the image is far away beyond C. Well, if it's at F, it's at infinity. For all intent and purpose, no image form. So what happens if we are in F? Well, how can we go one more step if the image is all the way at infinity, or for all intent and purpose, no image? What happens if it's in F and the mirror? So we'll take a look at this. We'll look at, okay, so in parallel, out through F. Okay, now remember that third ray we did. An object going through C reflects back upon itself. So we could look at that actually and draw that ray. So in through C, out through C. Or for that second ray where we technically go through F, there's kind of another way we could do that. It hits the mirror as if it went through F, so like as if it originated at F. So in through F, then reflects out parallel. So we have to set it up a little bit different. Now if you look at these rays all diverge on this side of the mirror, but they come together and converge over here. So if we extend these backwards, so if I extend this one backwards, so in parallel out through F, and again if it's behind the mirror we make it a dotted line, right? This one here, in through C, out through C. Now look at that, and go this one, extend this one backwards. Look what happens, ladies and gentlemen. They all converge to a point right here. So it actually does. So the other diagrams, the image is formed on the same side as the object, presenting a real image. At F, there is no image, it's at infinity. And if you go in F, we get a larger image, but it appears to be behind. And you can see all these images when you look into a spoon. If you get really close to a spoon, you'll notice that your image is really, really large and it appears to be behind the spoon. So location, behind mirror. Orientation, it's upright like the object. Size, larger than object. An image type, since it appears, we had to use the dotted lines to find it behind the mirror, so it is in fact virtual. So those are all the scenarios that we have for a concave mirror and various object locations. So if we look at the next page, we'll see a summary of that. So what do you see when you move your face close to the concave mirror? The image of your face is right side up and behind the mirror. So its orientation is upright and it appears to be behind. Concave mirror produces a virtual image if the object is located between the mirror and the focal point, as we saw there, inside that focal region. And we can see the same scenario here with those diagrams. But I didn't draw that third ray that I didn't really mention to begin with. But through F, okay, so we kind of assumed it came through F, here hits the tip, reflects out parallel. So this second ray is a little tricky drawing something when the object is inside F. So again, two rays are drawn to locate the image. As before, ray 1 is drawn parallel and reflected to the focal point. Ray 2 is drawn as a line from the point on the object to the mirror, along a line defined by the focal point. So yes, it's a line defined by the focal point, since we can't go through it. At the mirror 2, ray 2 is reflected out parallel. Note that ray 1 and 2 diverge as they leave the mirror, so they expand outwards, so it cannot be a real image. However, sight lines extend behind the mirror, converge, they come together behind the mirror, and that leads to a virtual image. All right, so we have that. So those are all the scenarios for concave mirrors. Let's look at convex mirrors, so mirrors that are bending away from you. So in the first part, we learned that the inner surface of a shiny spoon acts like a concave mirror. If you turn the spoon around, guess what? You got a convex mirror. The reflective surface with the edges that curve away from the observer. So that's considered a convex mirror. What do you see when you look at the back of the spoon? You could go and quickly grab one and see what you see. So over here, do the same thing. So the center of curvature is on the opposite side now, right? So to draw these, we do something very similar, the same type of lines. So the first one, in parallel. So in parallel. Now I can't go in the mirror. It reflects outwards as if it came from F. And we can extend this line backwards. I'm a little bit off here on my F. Let's see if I can fix that. There we go. Kind of messy, but notice only one case here that we're going to see. And then in parallel, but before, or sorry, in through F, but of course before it hits F, it hits the mirror and is reflected out parallel. And of course we extend that back and look what happens. There's an intersection point right here. So this is where our image is. Image. So of course location, behind the mirror. So no matter where I put this, because my F and C are on the opposite side, we just have the one case. So behind the mirror, orientation, it's upright. Size, it's definitely smaller than the object. Smaller than object. And image type, it is virtual. So you see an upright but smaller image of yourself. Properties of a spherical convex mirror shown in the figure on the top of the next page. So we'll stop the video now, come back, we'll look at that, and then finish up this section.